So all of these rules have led up to what's called a Lewis electron dot structure. And one of the great American chemists, his name was G.N. Lewis. And Lewis created these rules to try and figure out how electrons are distributed around molecules. And it's a very cool set of rules that we'll use a lot. The rules are pretty chill. And once you do that, you'll be able to see how electrons are placed around atoms in molecules. And that can be pretty powerful. And in a nutshell, Lewis had this set of rules to take the outermost electrons, which he called valence electrons. So valence just means outermost electrons. And you can take those outermost electrons and put them around the molecule as bonding pairs when you have lone pairs between two different atoms. I'll abbreviate them BP quite a bit. And also you can put electrons as lone pairs. And a lone pair is just a pair of electrons that are on a single atom. They're not being shared with anything else. So let's check out how a Lewis structure works. To figure out how a Lewis structure works, we have to talk a little bit more about valence electrons. So we talked in an earlier chapter about the total number of electrons in an atom, but not all of those electrons will be involved with bonding with other molecules. Some of them are deep inside the molecule. They're too close to the nucleus to make any bonds. However, some of them will be on the outside of the atom, and those are the ones that will make bonds to other atoms. So the valence electrons are the ones that are going to make bonds with other molecules and atoms. On the other hand, we'll talk about core electrons. Core are just too deep inside the atom to make connections with other atoms. So Lewis structures, we need to know how many valence electrons we have before we start building them. For main group elements, which is mostly what we're going to talk about in this section, and by the way, main group elements are the A groups mostly, so 1A and 2A on the far left, as well as 3A through 8A on the right-hand side. The number of valence electrons basically equals the group number. So let's look at some examples here. Carbon is group 4A on the periodic table, but we know from our earlier interactions that carbon has a total of 6 electrons. So this 4A, the 4 is what we're after. 4 means it's going to have 4 valence electrons. And since carbon has a total of 6 electrons, we can talk about the core electrons, which are the electrons that won't be involved with bonding. It's total electrons minus valence electrons. Carbon's going to have 2 core electrons. So 2 of carbon's electrons won't be involved with bonding with atoms at all, but those other 4 are going to be really important, as we'll talk about in a little bit. Bromine is in group 7A, so that means it has 7 valence electrons. Bromine has a total of 35 electrons, so 35 minus 7, bromine has 28 core electrons. Down here it shows actual electron configurations. This is for sodium. Now if you remember, sodium is 1s2, 2s2, 2p6, 3s1. And as the n number, 3, 2, 2, and 1, if you remember, as the n number gets bigger, the electrons get farther and farther from the nucleus. So sodium in group 1A has 1 valence electron. It's going to come from that 3s1 orbital. And that 1s2, 2s2, 2p6, that neon core, those are all core electrons. And honestly, they're boring for chemists. We don't really care about those. So valence electrons are just the outermost electrons. And you can go back to all the electron configurations. It's usually the highest n electrons that are involved in the bonding. So if I said, how many valence and core electrons does boron have? Well, boron is in group 3, 3 valence electrons. Boron has a total of 5 electrons, 5 minus 3, 2 core electrons. And likewise there in the bottom, fluorine has a total of 9 electrons, but it's in group 7A, so 7 valence electrons, 9 minus 7, 2 core electrons. So here's a kind of question you might see. It says, how many valence electrons are in phosphorus? All right, so phosphorus is number 15 on the periodic table, but what we want for this answer is we want to know what group it's in. And this is where it's really important to use the quote-unquote American version of the periodic table, where we have phosphorus in group 5A, not number 15. And that 5A means that it's going to have 5 valence electrons. So that's the advantage of the American quote-unquote periodic table, because the group numbers can literally tell you the valence electrons, and the valence electrons are used to build molecules, so that's why they're so important. This is an example of a Lewis structure for hydrogen monochloride, HCl, all right? And if you look at this structure, there's a line between the hydrogen and the chlorine, and that's called a bonding pair. And a bonding pair represents 2 electrons, so the H and Cl are connected by 2 electrons. It's like a handshake, all right? There's a bond between the H and the Cl. But Cl has a bunch of double dots around it. You can see there's 1, there's 2, and there's 3. And they call those lone pairs. Lone pairs are pairs of electrons, 2 electrons that are just around one atom. So HCl has 1 bonding pair between the H and the Cl, and the Cl has 3 lone pairs around it. And so this is what they call a Lewis structure, a Lewis electron dot structure. Now, bonding pairs should always be lines. Do not use dots for bonding pairs. That's a big no-no when it comes to chemists. On the other hand, lone pairs should always be dots. Don't use lines, all right? So make sure you follow this. This is important to chemists. Bonding pairs are lines. Lone pairs are literally dots. Don't use lines for them. Also notice that around the chlorine, there are 3 lone pairs and 1 bonding pair, for 4 pairs total. And we'll talk about this here in a little bit. But more or less, atoms want to have usually 4 pairs around them. Now, hydrogen does not. Hydrogen is so small, it's happy having just 1 pair. And we'll talk about this here in a little bit. We'll come back to this idea of 4 pairs around a central atom. So if you're going to build a Lewis structure like HCl or H2O or any other combination, generally speaking, the number of bonding pairs around an atom that's in group 1A through 4A will equal the group number. On the other hand, if you have an atom which is 5A through 7A, like chlorine, for example, the number of bonding pairs will equal 8 minus the group number. So let's think about that in terms of HCl. Hydrogen is in group 1A. It has 1 pair around it, and that's actually really happy. On the other hand, chlorine is in group 7A. So 8 minus 7, it wants to have 1 bonding pair, and that makes it pretty happy. And that's a pretty good rule overall. We're going to see there's some exceptions, but if you have to make a guess, that's a pretty good place to start. Except for hydrogen and a couple other things we'll talk about later, generally speaking, bonding pairs plus lone pairs will equal 4. So if you look at chlorine, chlorine has 3 lone pairs and 1 bonding pair. 3 plus 1 equals 4. Now, each of those pairs is 2 electrons, so 4 times 2 is 8. They call this the octet rule, and an octet rule usually results in a stable configuration of that particular atom. It's not always right, okay? We'll talk about that more later, but more often than not, if you can have an octet around your central atom, pretty awesome. However, we're already seeing that hydrogen only has to have 1 pair to make it happy. So it's not, as I said, perfect, but more often than not, it's great. In Chem 104, which is a lower version of chemistry than Chem 221, the octet rule is seen as the golden rule, all right? And almost always it's followed. But in our bigger class here, we'll see more exceptions as we go through. So let's build a Lewis structure for ammonia. Ammonia is NH3, and ammonia is a pretty important chemical in organic chemistry and in regular chemistry. You can buy ammonia, like in that bottle in the lower right-hand side from Kroger of all things. It's a great cleaner for household things. A lot of household cleaners have ammonia. But anyway, if you wanted to build the Lewis structure to see what it quote-unquote looks like, you would first start off by counting the valence electrons. So on the periodic table, which I would encourage you to have in front of you as we go through this discussion, nitrogen is group 5, so it has 5 valence electrons. Hydrogen is group 1. So when you're counting the electrons, there are 3 hydrogens, and each of them have 1 valence, and there's 1 nitrogen with 5. So ammonia has a total of 8 valence electrons. And if you divide that number by 2, it tells you that there's a total of 4 pairs of electrons. So we have 4 pairs of valence electrons to place around the NH3. And that's the first step you want to do. Now, the next thing you want to do is you want to figure out what the central atom of the molecule will be. And the punchline, it's never going to be hydrogen. So for NH3, that makes it obviously nitrogen because it can't be hydrogen. So this is kind of silly. Now, in other molecules we'll see that are a little bit more sophisticated, the central atom is always the atom of the lowest affinity for electrons. What that means is it's the lowest electronegativity atom that goes in the middle. But on a practical level, most of the time, the first atom listed in a formula is the atom that goes in the middle. So for example, carbon dioxide, everybody calls it CO2, nobody calls it O2C. And the reason for that is that carbon is the central atom. It's going to be in the middle. And ammonia, you can see here, is NH3, the nitrogen's first, so that's why it goes in the middle. Yes, there are exceptions. Sometimes the first atom listed is not the central atom, but often it is. Just kind of keep that in the back of your mind. But for this example, yes, nitrogen's the central atom, and we have 4 pairs of valence electrons to place around it. So what I would do is start with putting nitrogen in the middle, put the hydrogens on the outside, and then place a bonding pair between each of those outer atoms and the inner atoms. So there's one line right there, there's a second line between N and that H right there, and a third one right there. Now each of those is a pair of electrons, and the first pair like that is called a sigma bond. A sigma bond will have relevance to us later. A sigma bond is like a single bond, but it keeps the outer atoms from floating away from the central atom. Okay, think about it like that. Now, we had 4 pairs total, and we just put 3 pairs down to keep the outer atoms from floating away. So if you have any electrons left over, you first actually start by trying to put them on the outside atoms, but hydrogen only wants 1 pair, so there's nothing to do that. So if we have any left over after that, we'll put any lone pairs on the central atom. And nitrogen likes to have 1 pair of electrons. So at this point now, you can see that nitrogen has 3 bonding pairs and 1 lone pair. It has 4 pairs total. That's an octet. And nitrogen in group 5 wants to have 8 minus 5, 3 bonding pairs. And you can see that it does. It has 3 pairs to hydrogen. This is the Lewis structure for ammonia, NH3. So pat yourself on the back. You just did your first Lewis structure. Woo, I know you're excited. But anyway, it's a pretty chill process. If you follow these rules through, you'll have no problem. You'll be good to go. One rule about this: a lone pair, like the one on nitrogen, is usually a lot bigger than the bonding or shared pairs that go around it. So that lone pair on that nitrogen is going to take up a lot of volume, and it's going to push the other ones a little closer to each other. So shared pairs are smaller and lone pairs are bigger. And the 2 electrons in the unshared lone pair, they don't really want to be next to each other, so they take up a little bit more space. We'll come back to this idea here in a little bit. But anyway, for right now, you can see making a Lewis structure, it's not too bad as long as you know how many valence electrons there are and you can figure out what the central atom is. So here's the kind of question you might see, and it says, which of the following Lewis structures is or are correct? Okay, and there's a couple different ways to answer this, but for what we know right now, remember that most of the time the atoms want to have, the central atoms want to have an octet around them, and an octet means 4 pairs of electrons, and they can be lone pairs or bonding pairs. So for example, if you look at structure number 3 there with the phosphorus, phosphorus. That phosphorus is pretty happy because the phosphorus has 3 bonding pairs to the 3 hydrogens and a lone pair. So 3 bonding plus 1 lone pair, 3 plus 1, 4 pairs, that's an octet. So that one should be a happy molecule. And happier doesn't mean it's like skipping around in the sunshine. It means that it has a stable configuration of electrons. I should be a little bit more precise and probably not use flowery language, but what can you say? If you look at the one right below it, though, fluorine only has 3 pairs around it. It has 2 lone pairs and 1 bonding pair, but most of these like to have 4. So I don't think that HF would be very stable in this configuration. The same thing for the other 2 on the left-hand side. Like the oxygen right there has 2 bonding pairs, but that's it. And it needs to have 4, all right? So oxygen needs more electron density around it. And this one right here is similar to what we just drew, except that there's no lone pair on the nitrogen. And without that lone pair, that nitrogen has only 3 bonds. That's not an octet either. So I would say that the only one of these which is correct would be structure 3. All right. It has an octet around the phosphorus. The hydrogens have their 1 bond, so they're happy. Everything here would be in a stable electron configuration, but all the other ones are probably a little deficient when it comes to electrons around the central atom. So let's look at another example. This is for the sulfite ion. And sulfites are actually around a lot more than you might think. If you're 21 and over or 19 and over in Canada and you drink wine, and I'm not encouraging you to or anything like that, but anyway, a lot of wines have sulfites. And so in the upper right-hand corner there, that's the label from a wine bottle. Sulfites are often a preservative, and sometimes people are allergic to sulfites, so they have to be careful, et cetera, et cetera. Anyway, let's draw it. Let's see what the sulfite ion looks like. Now, the difference between sulfite and the earlier ammonia example is that sulfite has a charge, and we'll talk about that here in a little bit. To figure out the central atom, it's usually the first atom listed. It's always the lowest electronegativity atom. Oxygen is second only to fluorine, and there's nothing else as big as oxygen except for fluorine, so sulfur will definitely be lower electronegativity. It's going to be the central atom, but again, it's usually the first atom listed, just to be honest. Valence electrons. Both sulfur and oxygen are in group 6, so each of those has 6 electrons, 6 valence electrons. So sulfur has 6, there are 3 oxygens, and each of them have 6 for a total of 18 from the oxygens. But notice here that I added 2 electrons for the negative charge. Negative charges mean you have extra electrons. You want to add negative charges to your total valence electrons. And conversely, if you had a positive charge, you would subtract electrons. It's a little reverse from what you might think, but it's totally doable. So for this molecule, then there's going to be 6 for the sulfur, 18 for the oxygen, and 2 extra electrons from the negative 2 charge. That's a total of 26 valence electrons. And if you divide that by 2, you get 13 pairs of electrons. So the next thing you want to do, you want to connect the outer atoms to the inner atoms. You want to connect the oxygens to the sulfur. You're going to make what's called a sigma bond, which is just a single bond. Each of those lines connecting the outer to the inner sulfur is a bonding pair. So we use 3 pairs to connect them. That means we have 10 pairs of electrons are left. And what we'll do on the next slide is we'll put them on the outer atoms first. That's something that's always important. And if we have any left over, we'll put them on the inner atom. So when you do that, you can see what happens. We had 1, 2, 3 pairs around the first oxygen, and then that oxygen has an octet. 3 lone pairs and 1 bonding pair is an octet. We'll do the same thing for the next oxygen and the same thing for the third oxygen. So by doing the outside atoms first, all of the oxygens then have an octet. But we do have 1 pair left over, and if you have any left over, they go on the central atom. So even sulfur gets a lone pair, and that makes sulfur happy because sulfur has 3 bonding pairs to oxygen and 1 lone pair. That's an octet. So everything here is totally happy. And so this is the Lewis structure for sulfite. Now, sulfites are very important, like I said, especially for wines. And there are a maximum allowable levels of sulfites and stuff that are set up by different government things, which is interesting. And organic grapes wine, they sometimes have added sulfites. I don't know all the details about why they add sulfites to wines. But anyway, it is kind of interesting how they all go around. And again, people that are allergic to these things have to really pay attention to it. I had a friend that would only drink super organic wine in order to keep the sulfite level concentrations down. If you have a Lewis structure with a charge, a lot of times what people will do is they'll put the charges like this in a square bracket, and then in the upper right-hand corner, they'll put the charge, positive or negative. So sulfite has a -2 charge, so that's why there's a 2- up there. So if you see the square brackets, that's the convention to use when you have an ionic compound. Now, notice that this version of the sulfite ion has a double bond. We'll talk later about why it is a little bit better to have a double bond around sulfite. We'll talk about formal charges in a little bit. Just realize the structure on the left, there's nothing wrong with it, but if you want to get the best structure, then yeah, you do get a little bit better structure if you have a double bond. We'll talk about all this when we get to formal charges in a little bit. Carbon dioxide, super important, greenhouse gases, all that jazz. Let's do the Lewis structure. Central atom, going to be the first one. Lowest electronegativity, definitely going to be carbon. Now, valence electrons, we're going to start going through this faster. Carbon is 4 valence. Oxygen is 6, and there's 2 of them. So 4 plus 6 times 2, that's going to be 16 valence electrons, or 8 pairs. So when we make the Lewis structure, first thing we'll do, carbon in the middle, oxygen's on the outside, connect the oxygens to the middle one using sigma bonds. So that's 2 of the 8 pairs we just put down. Next thing we'll do, we'll put lone pairs around the outside atoms first, and if we have any left over, we'll put them on the inside. Well, oxygen likes to have an octet, so each oxygen is going to get 3 lone pairs. That gives it an octet. So both oxygens here have an octet, and they're happy. However, carbon here feels kind of left out because carbon wants to have an octet as well, and carbon only has 2 bonding pairs around it right now. So carbon is not going to be happy with this configuration. So if you come to this kind of situation, there's a way to give more electron density to your central atom. So what a person will do if they see this, if they see carbon without an octet, is we have to give that carbon more electron density. So what chemists will do when you're drawing a Lewis structure is they'll take a lone pair from each oxygen and start sharing it with the central atom. So you can see there on the right-hand side there, carbon dioxide actually ends up with carbon having 2 bonds to the first oxygen and 2 bonds to the second oxygen. Now, oxygen doesn't feel slighted really. It's taking a lone pair that was all by itself and sharing it, but oxygen can still count that pair. So the oxygens have 2 bonding pairs and 2 lone pairs for an octet, and they're happy. And the advantage now is that the carbon has 4 bonding pairs around it. This is its octet, so all the atoms in the molecule will have a more stable configuration with this version of CO2. Now, the second bond that's formed is called a pi bond, or it gets the Greek symbol pi. And this is different from the math pi 3.1416, etc., etc. This is just called a second bond, and it's a pi bond. So in the CO2 structure, the black lines you could think of as sigma bonds, and the red line you can think of as a pi bond. And a sigma plus a pi bond is what a double bond is. We have 2 double bonds around the carbon in CO2. So this leads us to questions like this that says, which of the following Lewis resonance structures is incorrect for N2O? We'll talk about resonance structures here in a little bit, but what I'm really more interested in you seeing is I want you to see which one of these structures is not a good Lewis structure. Now, if you look at all of them, and I would focus on the central atom, the nitrogen, you want to look for nitrogen to see if it has an octet. So in the first one there, nitrogen is like carbon in CO2. It has double bonds on each side. So that's 4 pairs of electrons around nitrogen, and 4 pairs is kind of the gold standard, if you will, for these things. So that would be a good structure for N2O. If you look at number 2, there's a triple bond, which would be 2 pi bonds and a sigma bond, by the way. But that's 3 pairs of electrons to the nitrogen and a single pair to the oxygen, 4 pairs total. So that nitrogen is actually legit as well. So again, note you can have double or triple bonds. Pretty kind of cool. In structure number 3, similar, except that now the triple bond is to the oxygen and a single bond to the nitrogen. Well, that's 4 pairs total around nitrogen, and that's okay. But if you look at structure number 4, that central nitrogen has a problem because that nitrogen has 2 bonds to oxygen and 3 bonds to nitrogen. Now that's 5 bonds total. And a real important thing to follow is that anything in that second period, so carbon, nitrogen, oxygen, fluorine, it can never have more than 4 pairs of electrons. So in structure 4, it has 5 pairs. That would be a disallowed combination of electron pairs around nitrogen. That would not be a good Lewis structure. So notice here that for a lot of these things, you have to keep them at 4 pairs or less. You can't have more than 4 pairs. We'll talk about this more in a little bit. So when it comes to double or triple bonds, there's all kinds of examples out there. And these are just a couple of examples that happen. So carbon dioxide we just showed had a double bond. This crazy thing is called methyl cyanide. It's actually used a lot in making compounds and stuff. But it has a carbon-nitrogen triple bond. That's the cyanide bond. And it's actually pretty strong. In the upper right-hand corner, we have acetylene, also called ethyne. It has a carbon-carbon triple bond. So there's double bonds, triple bonds, all kinds of different bonds are possible. Now, we remember from earlier, as the number of bonds goes up, the length between the 2 atoms goes down. So a double bond is shorter than a single bond, and a triple bond is shorter than a double bond. So the bonds actually get closer together as the number of bonds go up. And we'll talk about this more later, but it is kind of an interesting thing. You do have more energy when you have a double bond versus a single bond, and a triple bond would have even more energy than a double bond.